This is video 15 in the lecture on the design of reinforced beams. This lecture deals with T-sections in simple bending in ULS. Consider a rectangular section in concrete with tension reinforcement, the strain diagram and the stresses. Now, let's say we try to minimize the use of material under the condition that we keep the height of the section and we keep the capacity of the section constant. So what material are we wasting, are we not using? Clearly for concrete, you only use the compressive area and the concrete in tension you neglect. So it's too much material. So if we make a very small calculation and we say that the force in the reinforcement is equal to the force in the concrete, in the compressive force in the concrete, just an equilibrium, and transversal equilibrium, then you can estimate that the needed compressive area is only 30 times the area needed for the concrete. So if we know that, then you will see that by cutting away material, you save. And it gives you the same strain diagram and the same stress diagram. Of course, you can go one step further and then you only have a compression zone and a tension zone, but they have to work together. So that's why there's a dotted line. But these kinds of structures do exist, where this is steel, or when this is a rod, just a tension rod, and these are spacers, and this is a compression zone. So this type of beam has been used in the past. But the T-section is in fact nothing more, nothing less than an optimization of a rectangular section. Now, a T-section on its own, when it's isolated, this shape is rarely used in reinforced concrete. In pre-stressed concrete, yes, but in reinforced concrete, when you pour the concrete on the side, when you have shuttering, the T-shape is a little bit difficult. But what will happen is on site, if you have a floor, for instance, with beams and a slab, well, the actual behavior of the floor is in fact always a T-shaped action. It's one T-shaped girder next to the other. So indirectly, you have T-shaped sections that you have to calculate. Even for instance, for tunnels, it comprises, for the calculation in the longitudinal direction, it comprises of T-sections. The position of the flange does not play an important role. It can be centric or it can be, like here, eccentric. Now, we have a small problem when we are calculating T-sections. If this is a girder or a beam in a T-section, the dotted line is before loading and the full line is after loading. Then this behavior seems okay. But if you look from the top, you will see that this is the flange and this is the web, that the shear force keeps the flange to the web, but a little bit further from the web, the flange is less sollicitated. So the section before loading is not plane anymore after loading because of the difference in the shear force. So it's going a little bit skew. That's a problem because that was one of the assumptions that we had to calculate reinforced concrete. Now, what is the solution to that kind of problem is, what we will do is we will calculate with an effective flange width instead of with the real flange width. And where is this coming from? This is the web and this is the flange. You will see that instead of a nice uniform distributed load, compressive load on the flange, you will have peaks, a peak because of those shear forces. You will have a peak and then it goes down. So now you can assume now, if this is again the beam and then this is line, with these lines you see the equivalent compressive forces. You can see here, if you take now over a certain width, we take the compressive force constant. So we assume that for a certain width, the compressive force is constant. So at that moment, we can use beam theory. And this width we call effective width. So the effective flange width is the width of the beam over which uniform conditions of stress can be assumed, where this can be assumed to be straight. Consider now a floor slab supported by beams, and you have consecutive T-shaped beams to carry the loads of the slab. Now the effective width, where you can calculate the beam width, it is not just the center line of two beams, because this is too wide. The compressive force is not constant over this width. So to calculate the effective width, it is equal to 1/5 of the individual half of the distance between the two, the clear distance, half of the clear distance between the two beams, plus 1/10 of the length L0, which is the distance between the spots where the bending moment in the longitudinal direction is 0. And it should always be smaller than L0 divided by 5. Of course, the effective width of each beam, of half of the effective width of each beam, like this one, must always be smaller than the real width which is available. Also, the effective width of the beam is smaller than the real width of the beam. And it is the sum of the individual left or right, left and right, the individual effective width plus the width of the web. Now, let's try and do an example, then it will become clear. You have a floor slab supported by 3 beams. They have a clear distance of 2 meters. The beams have a width of 0.3 meters. And B here, the actual width of the T-section here is 0.3 plus half of the clear distances. That makes 2.3 meters. So this is 2.3 meters. It's an isostatic beam or an isostatic girder with a span of 6 meters. The effective width of the effective width is the left side of the effective width plus the right hand side plus the width of the web, and it must be smaller than the B that we calculated here. So on the left hand side we have 0.2 B1 plus 1.1 L0, and it must always be smaller than 0.2 L0. It means it must be and it must also be smaller than 1 meter because of this. Now, B effective is then 0.2 times 1, because this is 1 meter, plus 0.1 times 6, and it must be smaller than 0.2 times 6, and it gives you the effective width on the left-hand side of 0.8 meters, which is smaller than 1, so that's fine. That's okay. Also, the right-hand side is the same. There's no changes. It's 0.8 meters. If you look at the total effective width, it's left plus right plus the web width, and it must be smaller than 2.3 meters, must be smaller than that. So you will see that the effective width is 1.9 meters instead of the 2.3 that you should take in a natural way. You have a floor slab and you calculate the beams and you take half of the clear distance between the beams and you work with that. In reality, you must be very careful with that. Just do the check and only calculate with the effective width. L0, it's allowed to use a very simple formula to calculate L0, which is given in this picture. L0 is the distance between the points of zero bending. You can actually calculate it, but you can also use those approximations which are here. This approximation rule is only valid if this distance L3 is smaller than half of this span, and every span must lie between, let's say, 2/3 of the left-hand side and smaller than 1.5 times the span of the left-hand side. So the spans may not differ too much. For instance, a span of 1 meter and next to it a span of 10 meters. In this case, you cannot use those simplified L0 calculations. Now, if you do so, you will see that in a continuous beam or a continuous floor, you have different L0s in this section and different L0 in this section and different one here and another different one there. So it means that you have to calculate your beam with different effective widths. This is not very practical. So as an approximation, you can take the constant beam cross section with the effective width of the cross section in the span. For instance, here, sagging. So you can take L0 0.7 L2, and with this L0, you calculate effective width, and you can take the whole beam with the same effective width. Now, let's have some practical elements about this effective width. We have seen that T sections, not pre-stressed, that for T sections in reinforced concrete, you use it for floors, or you can use it for culverts or for tunnels with different sections. If you make the design, then you see here the clear distance B of the distance B and the clear distance S and the distance B. Here the same. The actual, let's put it this way, the actual width of the flange, and this is the clear distance S. Now, if you make a design, then you want to make it yourself easy, and it is easy for the stresses and the strains. So you want that the width B should be always smaller or equal to the effective width. Why? Otherwise, you will have some strange effects around this point. So it's easy for you, then you can calculate it as a T section, it's no problem at all. So you try to take the real width B smaller than the effective width B. Now, if you write down this condition and you write down the formulas, then you will end up, of course, that B1, the left-hand side, must be the real length of the left-hand side must be smaller than the effective length of the left-hand side, which is obvious. Then B1 is this with the formula like we have seen, 2B1 is then that. And we see here that if you take S, the clear distance between the two beams, if you take this clear distance smaller than 0.25 L0, then you can assume that the effective width is equal to the real width that you see on your drawing. So this is important for your if you put dimensions down, if you want to know how far should those beams be apart, in a bridge, for instance, how far should I put them apart? Well, just write this rule and say that the clear distance should never be more than a quarter of the clear span, a quarter of the span distance, L0. Consider now a T-section. BF, we call that the width of the flange, HF is the depth of the flange, and BW is the width of the web. And the definition of H and D and C, it's all the same as with rectangular sections. Now, how do we calculate in a simple way a rectangular section? In fact, it is simple. We take the superposition of two cases. The first one, it's the T-section, equals the rectangular section B times H. This is the total section B times 8, which is this one. And we subtract, because we have too much. We don't have this material here. So especially this plays a role. This material plays no role at all. But this material plays a role. So we subtract the rectangular B minus BW and H minus HF, which is nothing more and nothing less than those two rectangulars together make this. So, and then you got the T-section. So it's a superposition of two rectangular sections, and that's it. We know how to calculate reinforcement of rectangular sections, and then we will do it. But you must be careful because you don't know the domain where you are working in, but it's simple bending. So, or you are in domain 2A or you are in domain 1B. It's one of the two. And then you just, for the bending moment, you subtract the 2, and for the reinforcement, you subtract the 2. Also nice to know, if your depth of the neutral axis X is smaller than the depth of the flange, that means Xc is smaller than HF over D. If you have that, then of course it's the same calculation procedure as a rectangular section. So there's no difference at all, because all the concrete, or the most of the part of the concrete is in tension, and then you don't count on tension, concrete in tension. So it's the same as a rectangular section. This is in a lot of cases so. But if the depth of the neutral axis is bigger than the depth of the flange, then you have to calculate it with the procedure of a T-section. So now you can calculate for a T-section the needed reinforcement under simple bending. See you at next lecture.